Hi, welcome to 19th lecture on topology. Today we are going to talk about sequences and their convergence in a general topological space. I hope within this lecture I will finish whatever I want to say, but I just would like to make a principle statement. So in my humble opinion, sequences in general topology are not as important as sequences in a metric space context. Because the reason is whenever you deal with the sequences, finally what you end up with is convergence sequence. Okay, otherwise it's not going to give you any dividend, right? And so then you have to talk about the limit of the sequence. As it turns out, we are going to see it, okay, in this lecture, that the limit of a sequence is nothing other than adherent point of the range of the sequence, the image of the sequence. Therefore, whatever argument you want to deal with the sequences can be replaced, dealt with in terms of adherent points. That is why throughout my course, I have been placing a lot of importance when we talked about closed sets, closure of a set, density, various things. I always emphasize the adherent point. Okay, that's where even continuity also we saw that, right? Please keep that in mind. Okay. And but on the other hand, when you are a student of topology, you should learn that. Okay, you will also learn why sequences are not very adequate for general topology, though they are very good for metric spaces. Okay, right. So let us get started. This is my YouTube channel, as all of you know. Yeah. So let us get started. The first thing is, I'm sure all of you know what is meant by a sequence in a set. Suppose X is a set, a sequence in X is nothing other than a function X from natural number to X, and you denote Xn as the image of X at n, and we will call the ordered infinite tuple. This is X1, X2, Xn and dot dot dot. Okay, this we call as a sequence usually. Okay, and again, as I keep saying, many Indians still use this for a sequence. Okay, I don't like this for the simple reason, okay, this is a set notation nowadays. Okay, and also this is a much better, because when I write xn, this is okay, what I mean is infinite ordered tuple x1, x2, xn, etc., and so go on. So if I ordered n tuple, how will I denote x1, x2, xn? Put the bracket. Okay, complete the bracket. Here it's going to be x1, x2 dot 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 xn dot dot dot. So this notation is somewhat preferable. It's actually modern notation. Almost everybody in the world use only this notation, not this notation. Okay, anyway, now let's do that. Then suppose A is a subset of X, then I say xn, the sequence xn lies eventually in A, okay, if that there is an n, so that for every k greater than or equal to n, xk lies in A. Okay, that is what you call the tail of the sequence after the nth stage, after n minus 1 stage, if you want to be very precise. All the tail are completely lies in A. Then I say xn lies eventually in A. Okay, I'm just using this word so that it will be easier for me to keep saying later, whereas in analysis I may not say that, but anyway, right? Now let X tau be a topological space. Okay, suppose xn is a sequence. Okay, then when do I say xn converges to an x in X? We denote it by xn. I usually do that. I do not write limit n tends to infinity, etc. Again, I do not like that kind of notation. This is my notation. If at all I want to write, I will write limit xn. If you want, write n. Don't write n tending to infinity, because you want to say xn goes to in X. You want to define that you are defining n tending to infinity. This is even unknown object. You want to say what it means n going to infinity. These are all nonsense. So modern notation is just this. Okay, so I say xn converges to X if for every open neighborhood u of x, okay, xn lies eventually in U. What does that mean? That is, okay, there exists for every natural open neighborhood U containing X, okay, there exists a natural number N, so that for all K greater than or equal to N, Xk lies in U. That's it. This is very similar to the way you define convergence of sequences of real numbers. If Xn is a sequence in R, and when I say Xn converges to X, what I did was I formed an epsilon neighborhood around this. Okay, and I said there is a natural number, so that for every K greater than or equal to N, my Xn's lie here, right? And again in metric space also the same notation, right? So this is our definition of convergence. Okay, pause, review, proceed. Okay, good. Recording is going on. I just got over. Right? Okay. So what are the natural things you would like to look at? Okay. Let us look at some examples as usual, right? And you will also see why. Okay, let's look at examples. Okay, if I have a sequence xn which is eventually constant, what does that mean? That means there exists a natural number n, so that for all k greater than or equal to n, okay, xn equal to xn plus 1 equal to xk, that is for xk equal to xn for all k greater than or equal to n. Then I say eventually constant, namely the constant is x sub n. Usually we will say eventually constant. Okay, right. You follow that? So the first example is if xn is eventually constant, say with okay, the constant being x. So this xn we will call the constant term. That means what does it mean? X1, xn minus 1, I do not know. Some xn may even appear here, it will be same x and so on. That's how it looks like, right? Then we want to claim xn converges to x. That's very clear. Why? Give me any open neighborhood of x. Okay, now choose n. Then what do I know? For all k greater than or equal to n, my x n is going to be x that belong to you, right? Xk or k greater than or equal to n will be x, and therefore it belongs to you. You follow that? So that's the easy thing. Okay, second thing, let's look at the simplest case. If let x be discrete space, right? Now suppose you give me a sequence xn, right? Let me assume xn converges to x, right? You understand? Now I want to make use of the fact xn converges to x. So what should I look for? Give me any open neighborhood u of x, then I have to say something. Okay, my xn eventually lies in that neighborhood. Now what is the simplest neighborhood in a discrete space containing x? Obvious, right? Take the singleton x, right? Then what happened? There is a natural number n, so that for every k greater than or equal to n, my xk lies in the singleton x. That is same as saying for all k greater than or equal to n, my xk equal to x. That is same as saying, okay, xn is eventually constant. So what have we found out? If I have a discrete space, if I am given a convergence sequence, then it must be eventually constant. If it is convergent to x, then the constant must also be x. After a certain stage, all the terms of the sequence must be equal to the limit. Yeah, that x is called the limit. I didn't mention that, but okay, I'll let you know that. All right. Now let's look at. So what did you find here? So let us look at the first example. First example said any eventually constant sequence is always convergent, immaterial of the topological space. Do you understand that? Yeah, but what did we find now? In the discrete space, if at all there is a convergent sequence, it has to be eventually constant. What does it mean? It's something like saying any constant function is continuous, but there may exist a topological space on which the only continuous real valued functions may be constants. We have seen such examples. Do you remember in our course? So that's very extreme. But on the other hand, remember, on a discrete space, every function from a discrete space to any space is continuous. Compare and contrast. See, this is how you have to keep going back and forth so that you become confident of the subject. Okay. Now let us look at the other one. What should be the next example? I'm sure all of you know that it is in discrete space, right? Now suppose I give a sequence xn. Okay, this may be any sequence, right? Now start with any a in x. Okay, arbitrary a. Now the only open neighborhood which contains a in the indiscrete space is x, right? You understand? This is the only open neighborhood of a. So what do you think I got it? That means my entire sequence xn, okay, lies not eventually, completely in x, which is my u. Okay, that means xn converges to a, right? Now what did you find? So you gave any sequence. Let me underline the words, keywords. Okay, this is any sequence and this is any a, right? Give me any sequence and any a in there, then xn converges. That means how many limits are there? There are as many limits as the number of points, as many points in x, right? So that there is no uniqueness. If x has more than one element, okay, any sequence will converge to each and every element of x, therefore there is no uniqueness. Do you follow that? Pause, review, proceed. Now let's look at the fourth example. I think our favorite example will again take tau with the VIP topology. Of course, VIP is 0. Right? Now suppose I have a sequence xn, okay, here, and assume xn converges to 0. Right? Now you know what I should ask. How many of you can ask that question? Yes. What's the simplest open set containing 0? In the VIP topology, the U which contains 0, the simplest is singleton 0. So what does that mean then? That means if xn converges to 0, that means, okay, xn lies eventually in singleton 0. That means xn is eventually 0. Constant 0 sequence. Yeah? You understand that? Okay. Right. Now let me assume my xn yeah. Now let me assume my sequence xn converges to a and a is non-zero. Something very interesting is going to happen. By the way, go back to this example in discrete space and discrete thing. I already contrasted. Do you see that? In a discrete space, you take any function f from a discrete space to any topological space, it's always continuous. But on the other hand, if you give me a convergent sequence, it is essentially a constant. Eventually a constant is it's as good as a constant sequence. Do you understand that? Whereas let's look at indiscrete space. right? In indiscrete space it says you give me any sequence, okay, it converges to each and every element in the space. Compare these two things. Yeah, what do you know about continuous function there? Start with any topological space y, any function f from y to x will be continuous. Yeah, this has something lot more meaning, but I don't want to spend my time on that, but this is good enough. Let's come back to this. So suppose I have, now what is the simplest open set containing a, that is of the form a comma 0 in a VIP topology, right? Therefore what do I know? Since xn converges to a, xn lies eventually u, that is a comma 0. What does that mean? That means, okay, there exists a natural number n, so that for every k greater than equal to n, my xk is a 0 or a, that is xk lies in 0 and a. So what does, how do you picturize that? You picturize that like, I do not know what happens x to xn minus 1. After that this will be one of these two, okay, let us call this and let us call this, okay, it will be anything, you just have to fill it in, okay. I will use the same color so that it will be easier. Nothing, I don't care, right? It could be 0 or it could be a, you just to do that, then this has to be convergent. How many of you understand this? If it lies eventually, this has to happen. So if I give this, then any such sequence lies in this, right? But just because of this, make sure does such xn also converge to 0? Remember, xn converges to a is non-zero. Does an always converge to 0? You know the answer, because if f1 converges to 0, what does it mean? Xn is eventually 0. If so, then eventually 0 sequence. But that's not true, because I can put lot of a's in between. Do you follow that? Yeah, please pause, review, proceed. So I leave this exercise, okay. Outcast topology as exercise. Okay, investigate exactly, because now I had already given 18 lectures. If you have been diligently following my way of thinking, you should have reasonable confidence to work out, and do not be disheartened if you don't get any correct, any kind of a definitive answer and you are not sure about the answer. Do not worry about. The important thing is the journey that you tried on your own, that is more important, okay. If not today, after a few lectures you will figure it out also later, okay. So have confidence, go ahead, okay, do not give up, right. The next example, okay, let us look at R with lower limit topology. Okay, let me look at a sequence xn and a sequence yn, right. That let us say xn is 1 by 1 minus n, yn is 1 by 1 plus 1 by n, right. I want, so what is a natural question you would like to ask? Does xn converge to 1 in the lower limit topology? Does yn converge to 1 in lower limit topology? Right. So now all of you are good now, right? So what should be the question you should ask? What is the simplest open sets or typical open sets which contain one? Simplest and typical open sets, there are the form like this, one here and some 1 plus epsilon where b is strictly greater than 1, right? These are the typical thing. So if xn converges to 1, this xn, then eventually xn should lie here. That means xn must be greater than or equal to 1. That's not true. Do you understand? Therefore this is false, right? But on the other hand, let us look at this. Yn converges to 1 and y is 1 plus 1 by n, therefore it's always greater than or equal to 1, and if 1 by n is less than epsilon, then yn actually lies in 1 to 1 plus epsilon. Therefore yn lies eventually in this set. Do you understand that? So if 1 by n is less than epsilon, then 1 plus 1 by n will be less than 1 plus epsilon, right? Therefore by Archimedean property, choose an n so that 1 by n is less than epsilon. And for all k greater than or equal to n, 1 by k will be less than 1 by n, which will be less than epsilon. Therefore 1 plus 1 by k will be, and it's greater than 1. Therefore this lies in 1 to 1 plus epsilon. So the sequence yn eventually lies in the typical open and open set. Therefore xn converges to this. So this is the answer for this is yes. Yeah, you understand this? So pause, review, proceed. Okay. Right. So one more example, few more. As I said, it's good to look at a lot of examples so that after that, remember, as I keep saying, do not get worked up about whether you would remember any of these things. If you learn to think along with me, you will see it's very easy. You can just do everything on your own. At any given time, you can do it. So let us look at R with a co-countable topology. Did you see that? My comma always comes here, right? And suppose xn, okay, is a sequence here and xn converges to x. Yeah. Now do you see something very interesting? This is where you have to be creative. What are the open sets? The non-empty open sets are whose complement u is open here if u complement is, assume u is non-empty, u complement is countable, right? Now what are the typical open set, open neighborhoods of x? Okay, I have to take R and throw away a countable set. So in particular I could have thrown away all these xn's, right? I could have thrown away all these xn if xn is not equal to x, right? This is a countable set. Do you understand that? Yeah. Now what happens? Now suppose my xn, you said xn converges to x, that means okay, there is a natural number n so that for every k greater than or equal to n, my xk should lie here, right? When does xk lies here? Only if xk equal to x, otherwise it cannot lie. Do you understand that? If xk is not equal to x, then xk does not lie in u. Therefore if you say it lies, since xn converges to x, that means eventually the sequence xn must lie in u. That means there is a natural number so that for every k greater than or equal to n, my xk should lie in u. But if xk is not different from x, I have removed it, right? It's not in u. Therefore if you say it is, that means okay, xk must be equal to x for every k. That means xn is eventually constant sequence x, the constant being x. Okay, pause, review, proceed. What should be the exercise for you now? Cofinite topology. Yeah, this exercise for you. So in the order topology also I can do a few things, but I think we had already done. Okay, so I'll just look at only one more simple example. Let us look at I2. Okay, that is a 0 1 cross 0 1 with order topology. Okay, so I have this. Now let me look at n minus 1 by n minus 1 by n. This is my sequence x and yn in I squared. Yeah, now you can see that 0 0 when n equal to half, and when n equal to 1, 2 by 3 2 by 3 and so on. So what do you think you would like to ask then? Do you see the picture? So I would like to know whether x and yn converges to 1 1. That's a question I would like to ask. Yeah, right. So if I had gone through my order topology lectures, what is the simplest open set containing 1 1? This is my 1 1. Simplest open set is like this. That is the interval of the form 1 1 minus epsilon to 1 open interval, and this close. The basic open set is this semi interval. Okay, consider this as a point u. This is your v. Okay, this order. You understand this? So none of these things are going to be there. So the answer is no. We will proceed. Okay, all of you get it? Okay, now let's look at a very simple result. Okay, let me call it a lemma. Let x tau and if you want to call it tau x tau y be topological spaces. Okay, let x and be a sequence in x, so that x and converge to x. Okay, then let f from x tau x y tau y be continuous at x. Okay, then what do you think I want to conclude then? Okay, so actually it would be nice if you let x and be a sequence in x, so that x and converge to x, then f of x and is a sequence in y, and f of x and converge to f of x. Is that clear? Yeah, okay. Now let's go. The proof is extremely simple. No a kind of a difficulty. Okay, so let V be an open neighborhood of fx, right? I want to prove fx and converge to fx. What does it mean? I have to start with an open neighborhood B of fx and then show that the sequence of fx eventually lies in B, right? Okay, now so I know f is continuous at x, right? And B is an open set containing fx. Then therefore what do I know? Okay, since f is continuous at x, okay, there exists an open neighborhood u of x, so that for every z in u, f of z lies in V. That is f of u is contained in. Do you remember that? Yes? Yeah, very good. Now what is given? I know xn converges to x, and what is u? U is an open neighborhood of x. Therefore what do you think I will do? I will invoke the convergence of xn to x. Therefore there exists an n so that for every k greater than or equal to n, my xn lies in u. But if the moment z lies in u, I know f of z lies in V. That means, okay, for every k greater than or equal to n, fxn lies in V. Sorry, every k, right? Sorry, k. You understood? Therefore I have shown that the sequence fxn eventually lies in V. V's are arbitrary open set containing open neighborhood of fx. This implies fxn converge to fx. It's a very trivial proof. If you have gone through various analysis courses, etc., this is okay, utterly trivial. Alright. So what is the next question you would like to ask? Remember, in analysis, if you have gone through my analysis course or metric spaces, etc., there I have proved it. If f is a function from x to y, x and y are metric spaces. If f is a function, so in the metric space case, x and y are metric spaces, and f is a function from x to y, then f is continuous at x if and only for every sequence xn in x, so that xn converges to x, we have fxn converges to fx. Right? What we have proved in the general topological space is one way. If f is continuous at x, then we have proved any sequence xn so that xn converges to x implies fxn converges to fx. So we should ask for converse. Right? Is a converse true in general? Notice that the converse is true in a metric space. Arbitrary topology spaces. Okay, the answer is no. Sad. Yeah. Why? Let us look at. Yeah. Let us look at R with I think co-countable topology. Again, I don't know why my comma has to go always at the wrong places. Co-countable topology and R with usual topology. And we know that there is no connection between these two things. Right? Now let's look at my F to be the identity map. Yeah. Now I say F, okay, if xn, okay, is a sequence in R with co-countable topology, and if xn converges to x, then fxn converges to fx in R with the usual topology. I claim this. Okay, this is our claim. This is obvious. This is actually triviality. Just because I said claim, don't be intimidated. It's very easy. Because now let's look at, I have a sequence xn and co-countable topology, so that xn converges to x. Then what do I know about xn? Just now we saw. It was one of the last example, right? Last examples. If xn converges to x in co-countable topology, then xn is eventually constant. Right? Say xn equal to x for all n greater than or equal to capital N. Right? Now what is f of xn? Remember, f is identity, therefore f of xn is xn. Right? You follow that? Therefore, for all n greater than or equal to n, f of xn is same as f of x. Therefore f of x is also eventually constant, namely x. Yeah, therefore okay, f of x is convergent or with usual topology. Okay, pause, review, proceed. Right? Okay, so what does this mean? But f, I am claiming f is not continuous anywhere. Yeah, can you say why it's not continuous at 0, for example? Yeah, why it's not continuous? So are you following me? Okay, f is not continuous, and let me first say the usual thing for you. Okay, but I will say it's not continuous at any point later. Okay, if I want to say f is not continuous on this, that's very easy. Even if at one point it's not continuous, I am through. Do you follow that? Are you following? But what I want to show is f is not continuous at any point, but that can wait. Before that, let's go through this. This is very easy, because let's look at open set V, which is of the form, let us say 0 comma 1 open and double in tau of u, right? Therefore what is f inverse of V? That is again 0 comma 1, and this does not belong to tau of Cc, because the complement should be countable, which is not the case. Therefore f is not continuous. Do you understand this? Yeah, very good. Right, but I just want to know whether it is continuous. Okay, is okay, let me just look at the simplest case, the same proof. Okay, is f continuous? 0. Okay, so we want to know whether it's continuous at 0, right? Okay, so if it is continuous at 0, what is that I have to prove? Remember, f of 0 is 0. So what kind of typical open sets I have in TU? It's something of the kind, let us say minus epsilon to plus epsilon, right? So what do I have to find? I have to find whether there exists an open neighborhood u of 0 in tau Cc, so that f of u is completely contained in minus epsilon plus epsilon. Do you follow that? The same thing you can do with any a, you can do again whatever I am going to do. You follow that? The question is whether there exists such a thing, right? But remember, f of u is nothing other than u, and this is R minus a countable set, right? A is a countable set, right? Are you following? That means R minus A, okay, where A is countable. Okay, this of course is an open set, open neighborhood of 0, therefore 0 must be there. Okay, this should be contained in minus epsilon. Do you see a contradiction? Yeah, what is the contradiction? Now take complement, so that means R minus A complement should contain minus epsilon to plus A complement, and this is uncountable, and whereas this is A countable. This is a contradiction. Therefore what you had actually shown is f is not continuous at any point. I think probably I have done this in continuous maps. I had forgotten. Okay, right. Okay, now these are the things we have seen. Now let's go back. So what do you think I have shown now is that we have defined a sequence and its convergence, and okay, and we have seen that the uniqueness of sequence is not even guaranteed in the in the case of discrete space. Any sequence will be convergent and it will converge to each and every point of the space also. Okay, that kind of weird things happen. And similarly we saw in the VIP topology, if xn converges to a, the only thing is eventually all my xn's can be either a or 0. I don't care, but it will be convergent to a. You follow that? Whereas in some sense they are not good. And the third thing is, when I deal with continuity, if f is continuous at x, if xn converges to x, fxn converges to fx, but the converse is not true. That's the example which you saw. So all these examples, okay, prove the so-called inadequacy. Okay, that's not enough. It's not adequate. The sequences is not an adequate good concept as far as topology is concerned, right? Okay, there is one more thing about uniqueness of a thing. I would like to say when the uniqueness can be guaranteed. Uniqueness of the limit of the convergence sequence can be guaranteed. Okay, that all of you know, as in R, as in metric space, the same thing. How did I prove? Suppose I have a metric space, xg is a metric space. If xn converges to a and if xn converges to b, I want to say a equal to b. Okay, how did I prove? If a is not equal to b, okay, then distance between a and b is, let us say, equal to 2 epsilon, where f is positive. Then we looked at f of a epsilon intersection f of b epsilon. Then we know these two balls are, if you want it could even be less than this, I don't care. Okay, it may look like this, but if you want, but I don't care. Okay, but there is no point. This is open set, you remember? Because if z is here, that means distance between a and b will be less than or equal to distance between a and z plus distance between z and b, which is less than epsilon plus epsilon 2 epsilon, but this is equal to, therefore that's empty. Since xn converges to a, okay, there is n1, so that for every k greater than equal to n1, xn lies in ba epsilon, and similarly there is n2, so that xn lies in bb epsilon. Therefore for n1 plus n2, my k, my xk, this is k again, xk lies in ba epsilon intersection bb epsilon, which is empty set. This is a contradiction. Okay, that's how we proved. Now, so why, therefore we concluded in a matrix says if a sequence xn converges to a and b, then a must be equal to b. That is what is known as uniqueness of the limit. So if I want to give similar argument, what is needed then? Look, I go through the proof. I was able to find two open sets, ba epsilon and b epsilon. In the general topological space, instead of open balls, I should replace them by means of open sets. So given two distinct points a and b in the space, okay, then if there exists, assume that there exists open set u and b, u containing a and b containing b, so that u intersection b is empty. Then this proof will work. Do you understand that? Yeah. So suppose x tau has a following property. What is the property? Given a not equal to b, there exists u and b open and tau, so that a belongs to u. These are open sets, v, and u intersection v is empty. And now if you say xn converges to a and xn converges to b, then that should imply a implies, suppose p in q, then p equal to q. That's because if p is not equal to q, then I have a up and a uq open neighborhoods of p and q, so that up intersection uq is empty, right? But xn lies eventually in up, xn eventually lies in uq, right? Therefore there is an n1 here for the up and there is an n2. Look at any n greater than or equal to n1 plus n2, then that xn should lie in up as well as uq. That's a contradiction. Do you understand? Such spaces are called Hausdorff spaces. That is if this is a Hausdorff space, you will come to it later again. Then if a sequence xn converges, then its limit is unique. Okay, that's it. I just went through a little fast because these are all very trivial, and by now you are all MSc students, you should know these things very well. Okay. So but let's go back. What I said, I would like to reiterate. Okay, so what you have done is we have defined a sequence in a topological space and we define its convergence, and we saw, okay, the weird things can happen. Okay, there may be a sequence which will converge to each and every point, and any sequence may even converge, and there may be a sequence xn, okay, in the VIP topology which converges to a non-zero, but that means xn eventually is either a or 0, right? And there are sequences where it converges, eventually it's constant. And again, for continuity, sequences are not enough. Okay, any continuous function carries a convergent sequence to a convergent sequence, right? xn is convergent to x, that is a sequence, is a convergent sequence of xn. It is taken into, mapped into fxn is a sequence, that's again a convergent sequence. And does it converge to another point? No, it converges to fx itself. But what we saw was the converse is not true, right? Do all of you follow that? So these examples, okay, prove the study of sequences is not all that very important for topology. Oh, and again, as I said in the beginning of the lecture, whenever a sequence argument is needed, okay, I will replace it by something to the adherent point. Let me tell you what I usually do. If you give me general questions about topology, most often I will try to work out first in the case of metric spaces, because there is an distance function, real number, therefore I can estimate. Okay, I love analysis, so I will do that. If I find it difficult, then I will even go to Rn or R. Then I try to see whether I can generalize that argument, that proof, to general case. And if my arguments used to sequences and convergence nature of sequences, then I usually replace it by the limit point. Okay, then I usually replace it by the adherent point. Yeah, that's one point. You see, this is how things I keep forgetting. Okay, I'm sorry. The last thing, let me just stop with that. Yeah, this I said in the thing, I will prove it, but I forgot. Observation: if xn converges to x in any topological space, let's look at this xn. This is the range of the sequence. That is nothing other than the set x. Remember, a sequence is for us a function from capital X to small x, capital N to x. Therefore, this is the range of the sequence. Then x is an adherent point of the range. This is very easy. Why? This is very easy because you give me any open neighborhood of x. Okay, since xn converges to x, then I know there exists n, so that for all k greater than equal to n, xk all lie in u, right? So that means, are you following? That means xk which is in xn and it's also in u, therefore this is not empty. That means x is an adherent point of xn. Do you understand? So believe me, this is the simple observation. This is what I use whenever I think of a proof in the context of metric spaces or R or Rn which involve convergent sequences. When I want to generalize it to general topological space, most often I try to use this argument. Maybe I have to think of some argument which involves adherent points. I hope. Okay, we will see occasions. Okay, in fact I have been very successful in this. Okay, because in the general topology people claim that this is a sequence not enough adequate, and then they define other notions of convergence like net convergence, filters, etc. When I was an MSc student, I was also very much enamored. I fell in love with this, okay, more abstract concepts like nets and filters. I tried to prove their equivalence, how to go back and forth. I did a lot of things, but that was in my, and believe me, after that I never used them, because whenever I needed to use where the sequences will not be enough, then naturally all textbooks will try to make use of nets, which looks very similar to sequences. So many especially functional analysts will use nets. Okay, sometimes filters, so-called filters. I'm not going to torture you with those things. Okay, but what I find is I do not need nets or filters. Using this observation which I made, okay, I can prove those results. Okay, where sequences will not be enough, but I can still prove those results. Okay, if you look at my functional analysis book, one of the standard theorems is Banach-Alagolu theorem. There, all functionalist books will just like that use nets to get it. You will see that I don't need it. Anyway, you are all MSc students. I think this may make sense. That's why I said. But if it doesn't make sense, ignore. Simply ignore. But rest assured, whatever you deal with sequences, if you want to generalize the argument, look for an argument which uses adherent point. That is the pearl of wisdom I can give you. Okay, let me stop here. We'll meet again. I hope you enjoyed. Take care. Stay safe.